welcome to our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're going to start with the physics class 11, and that is your class 35. 34 we had done. So here in 35th class we have to start with unit 5, which is your laws of motion. That what we have to cover up here. Even though in the last classes we had done your law of inertia, and which is in detail we had discussed about it, and today we'll start discussing about the units that is Newton's laws of motion. In that we go ahead with the detail. Other than laws of inertia, we had done many more things related to the Galileo. So let's start it with the today's class, and before that, it's a huge request to all the viewers to please go ahead with like, share and subscribe so that maximum people can get the information at once, and even you can also enjoy the video as well. So here we go. Newton's first law of motion. So here in the Galileo, that simple but revolutionary idea that dethroned Aristotelian mechanics, a new mechanic that has to be developed, and the task was to accomplish almost single-handedly by Isaac Newton, one of the greatest scientists of all times. And Newton built on Galileo's ideas and laid the foundation of mechanics in terms of 3 laws of motion that go his name. Galileo's law of inertia was his starting point, which was formulated by first law of motion. So everybody continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. This is said by the first law of motion. Everybody continues to be in a state of rest or of uniform motion in a straight line unless compelled by some external force to set otherwise. Okay. So for that, the state of rest or uniform motion but implies zero acceleration. The first law of motion that can be therefore be simply expressed as if the net external force on a body is 0, its acceleration is 0. Acceleration can be non-zero. Only if there is a net external. Net external force on the body. Here are the two kinds of situations that are encountered in an application of the law in practice. In some examples, we know that the next external forces on an object is 0. In that case, we can conclude that the acceleration of an object is 0. For example, a spaceship out in interstellar space far all other objects and with all its rockets turned off have no net external force acting on it. On the same way, application of law in practice, in some examples we know that for that external here, the net external forces on an object is 0. In that case, we conclude that the acceleration of an object is 0. For example, a spaceship out in interstellar space, far from all other objects and with all its rocket turned off, has no net external forces acting on it. Where its acceleration, that is according to the first law, that must be 0. And if it is in motion, it must continue to move with a uniform velocity. More often, however, we do not know all the forces to begin with. And in that case, if we know that an object is unaccelerated, that is, it is either at rest or in motion, uniform linear motion, we can infer from the first law that the net external forces on the object must be 0. Gravity is everywhere for terrestrial phenomena. In particular, every object experiences the gravitational forces due to the earth. Also, objects in motion generally experiences a friction, viscous drag, etc. If then an object is at rest on its uniform linear motion, it is not because there are no forces acting on it, but because of various external forces that cancel it out, that is, add up to 0 net external force. You have to consider a book at rest on horizontal surfaces. It is subject to two external forces, that the force due to the gravity, that is its weight, acting downward, and an upward force on the book by the table. The normal force will be R. R is the self-adjusting forces. This is the example of a kind of a situation mentioned. That is a kind of a situation mentioned that what we had discussed. The forces are not quite known fully, but the state of motion is known. We observe the book to be at rest, and therefore we conclude from the first law that the magnitude of R equals that of W. The statement often encountered is that since W equals to R, which is your forces, that cancels, and therefore the book is at rest. This is incorrect reasoning. The correct statement is, since the book is observed to be at rest, the net external forces on it must be 0. According to the first law, this implies that the normal force R that must be equal and opposite to the weight. Okay. So basically, a book at a rest on a table and a car moving with a uniform velocity, the net force is 0 in each cases. Now you have to consider the motion of a car starting from a rest, picking up a speed, and then moving on a smooth straight road with a uniform speed. When the car is stationary, there is no net force acting on it. During the pickup, it accelerates. This must happen due to the net external force. Note, it has to be external force. The acceleration of the car cannot be accounted by any of the internal forces. This might sound surprising, but it's true. The only conceivable external force, along with the role on the forces of friction, it has been the frictional forces, that the acceleration of the car as a whole. You will learn about the frictional in the next topic of this unit only. When the car moves with constant velocity and there is no external force, the property of inertia contained in the first law of evident in many situations. Suppose we are standing in a stationary bus and the driver starts the bus suddenly. We get thrown and we get thrown backward with a jerk. Why? Our feet are in the touch with the floor, and if there was no friction, we would remain we were where we were, and while the floor of that bus would simply slip forward under our feet and back of the bus would hit us. However, fortunately, there is some friction between the feet and the floor. Its start is not too sudden, that is if the acceleration is moderate, and that the frictional forces would be enough to accelerate our feet along with the bus. But our body is not strictly a rigid body, and it is deformable, that is it allows us some relative displacement between different parts. What this means is while our feet go with the bus, the rest of the body remains where it due to inertia. Basically, relative of that bus therefore be thrown backward. As soon as that happens, however, that the muscular forces on the rest of the body by the feet come into play to move the body along with the bus, and a similar thing happens when the bus suddenly stops. Our feet stops due to the friction, which does not allow relative motion between feet and the floor of the bus. With the same way here, but a body is not strictly a rigid body, it is deformable, that it allows some relative displacement between different parts here. What this means is that while our feet go with the bus, the rest of the body remains, whereas due to the inertia relative to the bus here, therefore we thrown backward. As soon as that happens, however, the muscular forces on the rest of the body by the feet come into play to move the body along with the bus, and a similar thing happens when the bus suddenly stops. Our feet stop due to the friction, which does not allow relative motion between the feet and the floor of the bus, where the rest of the body continues to move forward due to inertia. We are thrown backward, and the restoring the muscular forces again come into play and bring the body to rest. Now we go for the question here, which is another important question, and the first question of this particular unit. The question is, an astronaut accidentally gets separated out of his small spaceship, accelerating in interstellar space at a constant rate of 100 meters second inverse. What is the acceleration of the astronaut the instant after he is outside the spaceship? Assume that there are no nearby stars to exert gravitational force on him. Let's get started. So here we go. The question we have: an astronaut accidentally gets separated out of his small spaceship accelerating in interstellar space. at a constant rate of 100 meter second square per square. What is the acceleration of the astronaut? The instant after he is outside the spaceship. Outside the assume that there is no nearby stars. To exert gravitational force. On him. So for that, first we have to find out the answer. I will tell you. In that, here, since there are no nearby stars to exert gravitational force on him, and the small spaceships exert negligible gravitational attractions on him, the net force acting on the astronaut once he is out of the space is 0. By the first law of motion, the acceleration of the astronaut is 0. Here we go. So since there are no nearby stars exert gravitational force, on him, and the small spaceships exert negligible gravitational attraction. On him. The net force acting on the astronaut once he is out of the spaceship is 0. By the first law of motion, the acceleration of the astronaut is 0. Now we will discuss about the Newton's second law of motion, that has been the important one. So that we will discuss in the next coming class. So stay tuned with us, and please like, share and subscribe so that many and maximum people can get the information at once, and even you can also enjoy the video as well. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Next in our class we will discuss about the Newton's second law of motion in terms of related to the momentum and all that detail. Thank you. Stay tuned.